Right. So what you need to remember, only two golden rules you need to remember when you are solving a circuit, right? Using operational amplifiers, right? Those are, as I said earlier, right? The first one is, right, an ideal operational amplifier does not draw any current in the amplifier, right? So if you have an operational amplifier, right, so the current entering into the operational amplifier is always zero, and whenever it has a feedback circuit, always your minus and plus terminal voltages are equal, right? If it is V minus and V plus, V minus is always equal to V plus, right? But this is true only whenever it is connected to a feedback, connected with a feedback network, right? So these are the two laws you need to remember whenever you are solving an operational amplifier circuit, right? You can solve almost every operational amplifier based circuit using these two, right? So let's see about an inverting amplifier first, right? An inverting amplifier. Right, you have done the practical on this one, right? You have already done the simulation practical on operational, the inverting amplifier, right? So now I'll draw the circuit, right? So this is your output, V out. Right, and then I have my inverting and non-inverting terminal. This is your inverting terminal. What I'm going to have is, I'm going to have a resistance here, and then here I am going to have my Vs or V in, right, which is grounded, right? I am going to ground my non-inverting terminal, right? Also, I am going to have a feedback resistance between my input and output. Let's take it as Rf and this as R in. This is Vs and V out. Right. Now, let me try to develop a relationship between V out and Vs, right? This is Vs. Okay, Vs using the two golden rules, what we have seen earlier. Right. What is the first golden rule says? Yes, there is no current entering into the operational amplifier, right? So I equals 0. Right, there is no current entering into the operational amplifier. So at this point, if I mark this current as if and this current as I in, right, I could say there is no current going into the operational amplifier. So if I apply Kirchhoff's current law at this point, I in must be equal to, yeah, minus if, because this is in the opposite direction, right? So there, since it is the other way around, I can say that if I apply this one, both are incoming currents, right? So I can write it as I in plus if equals 0. Am I right? They are coming into the node, so both of them have same polarity, they are positive, but no current is going inside the operational amplifier. So addition of these two, current is equal to 0. So I can simply write I in equal to minus if. Clear? I in equal to minus if. Similarly, I have another hint as well. So what is the voltage at non-inverting terminal? This is directly grounded, am I right? So I can say that V plus is equal to 0. Am I right? Why? It is directly grounded. If V plus is 0, see here there is a feedback resistance, and I can immediately say that my V minus, which is also going to be 0, right? Which is also going to be 0. If this voltage is 0, we can easily define IF, right? So if it is 0 and V out, so what will be my IF? Right, if will be the potential difference between these 2 points and divided by the resistance. So I can simply write my if is equal to, here V out, here 0, right? So V out minus 0 divided by the total resistance will be Rf, right? So simply that is equal to V out by Rf. Clear. Similarly, look at here. At this point, we have Vs, right? I have Vs here and 0 here. I can easily divide my I in equal to Vs minus 0 divided by R in, right? Or simply I can write it as Vs by R in, which is equal to my I in. Now substitute this one and this one in this equation, right? So I could say that I in is actually Vs by R in is equal to minus V out by Rf. Clear, right? Simply multiply this one and bring this the other side. I could say that, right? V out by Vs, right? This is what I need, right? I'm bringing this one here, this one there, and then bring the minus the other side, minus Rf by R in, right? Or in other words, I can say that what is V out by Vs is the voltage gain, right? Output voltage by input voltage, which gives you the voltage gain is equal to Rf over Rin. Or in other words, I can simply write it as V out is equal to minus Rf by R in into Vs. Am I right? So your V out is Rf by Rn times Vs. Now, for example, if Rf is 10 kilo ohm and Rin is 1 kilo ohm, then Rf by Rin becomes 10 kilo by 1 kilo becomes 10, right? 10 times of Vs. And also we have a minus here, right? This minus represents the phase shift, right? For example, if I have a waveform something like this, it will create a 180-degree phase shift and the magnitude will be increased something like this, right? So if this will be V out and this will be Vs, right? Look at here, whenever you have a positive half cycle, you will have negative half cycle. Whenever you have negative half cycle in the input, you will have a positive half cycle in your output, right? So this is how the 180-degree phase shift comes from, right? From this minus symbol, right? Also, the Rf by Rin creates the voltage gain. Clear? Is it okay? Right? So if you have any doubts while I'm doing, please ask me immediately, right? So the same thing, you have done it in your practical, right? You have practically observed it, right? And now you are seeing the, sorry, the mathematical or the derivations, right? So this is called as inverting amplifier because it also amplifies the signal and then inverts it, right? Just multiply it by a minus, right? That's why we call it as an inverting amplifier. Now let's see about a non-inverting amplifier. Right now, we'll see about a non-inverting amplifier. Non-inverting amplifier is nothing but a same circuit, right? But we have a potential divider at the output, right? And then I will have my Vs there. This is connected to it, right? Let this be minus and this be plus. right? So this is my V out. Let's take it as R1 and R2. Look at this one. This is just a potential divider. Am I right? This is just a potential divider. Again, this is the circuit, right? You can redraw the circuit into some other ways as well, right? Right, so the same circuit can be drawn in different ways, right? Look at this one. This is the circuit. I can draw this one something like this as well. Sorry. I'll draw it again, right? No. Right, so what I can do is I can redraw the circuit something like this, right? You must be able to differentiate it. R1, R2. Again, look at here, this one, they are same circuit, right? They are same circuit. But simply I have moved this one there, right? You must be able to identify the circuit configurations. Right, now let's see how we can solve it. Right, so now assume that the voltage at this point is V. Right, what is this? This is just a potential divider where you have V out and here you have 0. So what will be my V? How can I write my V? Using potential divider theorem, V will be R2 divided by R1 plus R2, right, into this one minus this one. I can write it as V out. Am I right? So V equals R2 over R1 plus R2 into V out. If this voltage is V, what is the voltage at this point? Is also V. Am I right? And look at here, there is a feedback path. So it should be, the terminals must be perfectly matched. What is the voltage at this point? If you have Vs, the voltage at this point will be Vs. Right? So using the second theorem, Vs must be equal to V. The second golden rule says Vs must be equal to V, and that is equal to R2 by R1 plus R2 into V out. Right? I can remove this one and I can simply write my V out equals, right, V out equals, this will go on top and this will come down, right? I can write it as R1 plus R2 divided by R2 into Vs. Am I right? Am I right? So again, I can rewrite this one, right? I can write it as R1 by R2 plus R2 by R2, right? R2 by R2 becomes 1, and hence I can write my V out equals, right? So R2 by R1, R2 becomes 1 plus R1 by R2 times of Vs. Am I right? Now look at here, there are no minuses, right? There are no minuses. Hence, if you apply a waveform, something like that, your output will be magnified with the same phase, right? They will be in phase. Your Vs and V out both will be in phase. And again, the gain will be equal to 1 plus R1 by R2. For example, if R1 is 10 kilo ohm and R2 is 1 kilo ohm, and then your gain will be 10 by 1, which is 10 plus 1 into Vs, right? So your voltage gain will be 1 plus 10, 11. Clear? Your voltage gain will be 1 plus 10, 11. Right? For example, if, right, if, Yes, if R2 becomes infinity and R1 becomes 0, right? If R2 becomes infinity and R1 becomes 0, what will happen to this equation? Right, which means R1 equal to 0 and this becomes infinity. What is 0 by infinity? Will be again 0, right? So 1 plus 0 becomes 1, right? 1 plus 0 becomes 1. So I can write that if R2 equals infinity and R1 equals 0, my V out is going to be 1 plus 0 times Vs, or directly Vs, right? If I mark that one in this circuit, R2 infinity means that circuit will be completely removed, and R1 is 0 means that has to be short circuit, right? So I'll redraw the circuit somewhere here, right? So this will be something like this, my plus minus, this will be my Vs, and then this will be my plus, because R1 which is 0, right, and then R2 infinity means that is pulled off, right? This is my V out. At that point I can see that my V out is equal to Vs, right? V out is equal to Vs. So we can say that the V out exactly produce the same Vs, right? It is called as the voltage followers, right? Because it just produced the same thing, right? So hope it is really simple, right? Using solving operational amplifier based circuits are really simple, right? I'll try to solve another circuit, right? And yeah, an analogues adder. Analog adder or analog summer, right? Analog summer. Consider a circuit, right? I'm drawing a circuit. Just yeah, this one, let this be R1, right? And here I have a point voltage of V1. This be V2, and I have a resistance R2, and up to I have Vn and Rn. I have a sequence of resistance and I'm just connecting them together, then giving it to an operational amplifier, an inverting terminal plus, which is connected to ground, and then I have a feedback resistance R, right? Let's take it as, okay, make it as RF, right? Since it is a feedback resistance. This is my V out, right? Consider this circuit. So I can say that the first golden rule says no current is going inside the operational amplifier, right? I equals 0. Again, the second golden rule says, yeah, the voltage at this point is always equal to the voltage at this point, and that is 0, right? If it is grounded, the voltage at this point is 0. Again, then the voltage at this point is also 0. Now, mark this current as the same IF, right? Same IF, and the current at this point as I, right? So I could again write that IF plus I equals 0. See, they are incoming currents. Both of them are coming to the node. So I am adding them, but it is not going through this one, right? So I is 0. Hence, I can write it as IF plus I is 0. Or I can write it as I equals minus IF. Clear? Okay, now the voltage at this point is 0. The voltage at this is 0. Hence, I can write it as 0 potential, 0, 0. Am I right? Along the whole wire, I am going to have 0 potential. Let me calculate the current through each branches. I1, I2, up to IN. So what will be my I1? I1 will be simply V1 minus 0 divided by R1. Am I right? So I1 equals, right, because here V1, this is 0 voltage. So the voltage across the voltage difference across the resistance is V1, and the value of resistance is R1. So I can write it as V1 by R1. Similarly, my I2 will be V2 by R2, and up to my IN will be Vn by Rn. Clear? Right. Again, I can say that my I, right, is equal to the addition of all these branches. Am I right? Addition of all these currents. So I can say that my I is equal to I1 plus I2 up to IN, which is again equal to minus IF. Clear. Now I can substitute each of the equation in this equation, right? In this one. So I can simply write my, okay, I1 becomes V1 by R1 plus I2 V2 by R2 up to plus Vn by Rn is equal to minus, again, what is my IF? IF will be V out minus 0 divided by RF, right? So minus V out by RF, right? So I can simply write my V out is equal to minus RF into, right? Because this RF is going there, into V1 by R1 plus V2 by R2 up to plus Vn by Rn. Clear? Vn by Rn. Right? So this will be my final equation. Now, if R1 equal to R2 equals R3 dot 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 equals Rn, then all these equals, right? And that is equal to Rf, right? Which means all these resistors are equal to Rf. So what I can do is, when I am multiplying each of them, Rf, R1 will get cancelled, R1, R2, R1, R3. So I can simply write my V out as, everything will be get cancelled. So minus of V1 plus V2 up to Vn, or else I can write it as V out equal to minus of sigma I equals 1 to N V I, right? V I, right? So this circuit, if all these resistance are equal, this circuit will produce V out, which is equal to the summation of all these voltages. Am I right? So that's why this circuit is called as an analog adder. Clear? Right. Similarly, we can have analog differentiator or analog subtractor. Right? I will share the lecture notes and practice the analog subtractor by yourself. Right? I am leaving it to you for your practice. Right now, let's see another circuit. Right? So just consider this one. Right? This is my V S. Right? And now I have a capacitor here. Minus plus. V out. This is R and this is C. Right. What type of circuit is this? And can you derive a equation or relationship between V out and V in? Right. Shall we try? Of course. Right. So let this be a time varying current. Right. We know that if your capacitor will be open circuited if we apply a Vs which is constant. So let me consider the voltage as V of t. Right? So I am assuming that the input is a time varying current. Clear? I'm assuming it as a time varying current, right? So in a capacitor, the charge, total charge served in a capacitor Q equals, I can write it as C into V. Am I right? C into V. What is Q? The total charge served in the capacitor. C is the capacitance of the capacitor. V is the voltage across the capacitor. This is connected to 0, right? So this will be 0, and again I can say that the voltage at this point V minus is also equal to 0. Hence, what is the voltage across the capacitor? Will be my Vt and 0, right? So V of t. So I can write my Q equal to C into V of t. Am I right? Just differentiate both sides with respect to time. I can write it as dq by dt equals C into, because C is a constant, right? This many millifarads, microfarads, or whatever, right? So C is a constant. I can write it as d dt of V of t, right? I'm just multiplying, just differentiating with respect to time, d dt of V of t, since it is a function of time, right? The input voltage V is a function of time. Now, what is dq by dt? Is simply your current I. Am I right? Rate of change of charge, right? Rate of flow of charge is called as current. So I can write dq by dt as I, or equal to C into d dt of V of t. Okay, now apply this one there. So if I mark it as I can say that the current I is given by this equation. Am I right? If I mark this current as I, and that is given by this equation. Right now, mark the feedback current. Let this be IF. IF is simply V out minus 0 by R, right? So I can write it as IF equals V out by R. Right, again, I'm going to apply Kirchhoff's current law at this point. Right, both are incoming currents, so I can say that I plus IF is equal to 0. Right, I is this one, right? I is C into d dt of V of t is equal to minus IF, which is V out by R. So I can write my V out as, just cross multiply this one and bring the minus the other side. So minus RC into d dt of V of t. Right. At this point, if RC equals 1, right? For example, R is 1 kilo ohm and C is 1 millifarad, then I will get R into C, which is equal to 1. If RC equal 1, I can rewrite this equation as V out equal to minus d dt of V of t. Right? So I can simply say that my output is the minus of the differentiated version of my input. Am I right? My input V of t is being differentiated when I am giving it to this circuit, right? So I can call this circuit as a differentiator or an analog differentiator, right? This circuit is called as an analog differentiator. Right? The circuit is called as an analog differentiator. Give me a second, guys. I'm receiving Sorry guys, right? So this is a differentiator or analog differentiator. Right. Now look at here, you have your capacitor here and resistance here. Let's see what will happen if we interchange the resistance and capacitance. Right, so now I am going to have my resistance at the input terminal, which is minus, plus, grounded, and then I am going to have my capacitor across the output. This is my V out, this is my Vs, R and C. Always remember, whenever you are drawing a circuit with operational amplifiers, these minus and plus signs are very important. Right? Without these minus and plus signs, your circuit is meaningless. Right? You will lose all the marks. Remember, whenever you are drawing a circuit, you must add these minus and plus. Right? Okay. Let's see now how we can solve this circuit. Right? Let this be I. Right? This be I. Right? And then this be IF. I can simply say that I is equal to Vs minus 0 because this is 0, hence the voltage at this point is 0. Vs minus 0 becomes Vs, so Vs by R. Am I right? Similarly, I can write my IF equal to, as I said earlier, I equals C into d dt of V across the capacitor. Am I right? So C into d dt of V across the capacitor. Right, so V out minus 0, right, so will be V out. Of course, this V out must be a function of time, right? It's a function of time, but we'll mark it as this one, right? Since it is Vs, we'll mark it as Vs, right? So I can say this one, and again by applying Kirchhoff's voltage law at this point, both currents are incoming currents, so I can say that I plus IF is equal to 0. Right, so I can simply write I is equal to minus IF, right? So Vs by R is equal to minus C into d dt of V out, right? d dt of V out. Now I need to take the equation in terms of V out. Am I right? Just cross multiply this one. No, take derivatives both sides. So I can write this one as, bring this R there. So this becomes RC, right? And then this one there. So I can simply write it as Vs and then dt, right, into dt equals minus, sorry, RC into, write this R into C, right, into D of V out. Am I right? Into D of V out. Now integrate both sides. RC is a constant. Am I right? RC is a constant. Now just integrate both sides. Right? So dV out becomes V out. Right? Integration dV out becomes V out. So I can write my V out equals, bring the minus the other side, RC becomes 1 over RC into integration Vs into dt. Am I right? Look at this one. Again, if RC equals 1, then my V out will be equal to minus of integration Vs into dt. Right? So if R into C in this circuit is equal to 1, then my V out is the integrated version of my Vs. Right? So minus of the integrated version of my Vs. Hence, I can call this circuit as an integrator. Right? This circuit as an integrator. Right? So actually, that's all about this chapter, right? There are about 6 circuits, and yeah, you guys all join the join in the Google Classroom, right? I will send the link in WhatsApp, and I will upload all the lecture notes, recordings, and sorry, lecture notes in Google Classroom itself, right? So I can, otherwise I can share the other link to you, right? You can refer that one. Okay. So hope now you have a clear idea on what you studied about operational amplifier and what you have done in your practicals about operational amplifiers, right? If you have any doubts, you can ask me now. Right. So hope, I think you all are clear about it. Okay. So join in the Google Classroom. I will send you the links and details to WhatsApp, and then I will upload the lecture notes as well. Okay. Right. Thank you. So yeah, the next class will be on Wednesday morning at 8 o'clock, right? Again, as I said earlier, I will start at a bit late, right? I will start at maybe about 8:15 or something. Okay. Thank you.